Brian is going to try and work out how much a galaxy weighs by adding up all the stars. I'm going to use a different approach. I'm going to try and use acceleration to measure mass. So this seems a bit strange. What has acceleration to do with mass? Well, we need to remember two laws of physics. The first is force equals mass times acceleration, Newton's second law of motion. This means that if something is accelerating, there must be a force, and they're in the same direction, so if you can measure the acceleration, you can calculate the force. Now in space, the only force is usually from gravity, so we also know Newton's law of gravity. Force equals g, mass of the two interacting objects, over distance squared. Set them equal to each other, and we find that the acceleration of an object is gm over r squared. So it's telling us what the mass is of whatever that's pulling it, constant, 1 over distance squared. So if we can measure how things are accelerating near some big mass, and we know how far away they are from the big mass, that should allow us to work out the mass. Okay. But how do you work out the acceleration of something in deep space? Well, what is acceleration? Acceleration is the rate of change of velocity. So what that means is whenever we see something with its velocity changing, then there must be an acceleration, and therefore there must be some mass nearby. And if we can see how much the velocity is changing, that will tell us how big the mass is. Okay, so what would you actually look at? Well, let's say you could see something moving through space like this, and after a while, let's say it's going in the same direction but faster. In this case, a small velocity has changed to a big velocity. That's telling us it's acceleration. We can work out how big it is by plotting the initial velocity vector and plotting the final velocity vector starting in the same place. And the difference is the acceleration. So in this case, the acceleration is pointing in this direction, so that means there must be some mass up around here, which is sucking things in and causing it to accelerate. And by looking at how big this change in velocity is, you can work out how massive this thing, whatever it is, up there might be. Let's say something was flying along like this, and after a while it slowed down. In that case, the initial vector is this, the final vector is that. So to go from initial to final, you now need an acceleration vector this way. So that's telling us in this case, whatever it is that's applying the force, this mass, must be back in this direction somewhere. So it's applying a gravitational force back there, in the same direction as this, pulling it back. And let's say you saw an object initially, say, moving this way, and after a while it was going at the same speed, but it changed direction. Velocity is a vector, so a change in direction still requires an acceleration. In this case, the initial velocity is like that, the final velocity is like that. So to go from one to the other, you need something like this, which means the acceleration is that direction, so the mass, whatever it is, must be over here somewhere. So that's what we're going to do. We want to work out how much a galaxy really weighs. We find something nearby, measure its acceleration, and we will use the equation acceleration equals g mass over r squared to go from the acceleration to calculate the mass.